So let's consider now another example of the 1D heat equation, except in this example, let's put the left end of the bar in ice water and the right end of the bar to be insulated. If you remember, when an end of the bar is in ice water, that means that the temperature is held at a fixed value for all time. So for example, in ice water, the left end would be held at 0 temperature for all time. If an end is insulated, then it's not the temperature that's held fixed, but rather it's the derivative of the temperature with respect to x that is held fixed. And in particular, that's held at 0. So no heat is flowing into the bar at the right end. That's what that condition tells us. So let's try and solve this 1D heat equation with these different sets of boundary conditions, and then an initial conditions given here, something that looks like 3 sine of 5 pi over 2L times x. Since we've modified our boundary conditions, we need to go back and redo the separation of variables strategy that we had used for the heat equation before. But actually most of it we're pretty comfortable with. In fact, the first few steps, taking an ansatz of x times t and plugging that into the partial differential equation, well, that part doesn't really depend on the boundary conditions. But the value of the separation constant does depend on the boundary conditions. So we're going to pick up there. So in particular, by making our ansatz and plugging that ansatz into the differential equation, we get these two differential equations, x double prime over x is equal to lambda, and t dot over t is equal to alpha times lambda. And we're supposed to use our boundary conditions to determine the sign of the separation constant. As before, we can have 3 different types of values for lambda. Lambda could be 0, lambda could be negative, or lambda could be positive. You're going to examine lambda equal to 0 and positive in a separate context on, say, a homework. So let's focus right now on lambda less than 0, which means that our x function is a cosine of kx plus b sine of kx.